A short demonstration, short presentation about Scala and in relation with data mining, right? We'll pick an algorithm from the clustering algorithm, and we'll try to implement it in this session. Yeah. Okay, let's start with a simple analogy, right? As a developer, what is the best way for you to learn a new tool or technology or language? And in my view, one of the best ways to do it is to pick a well-defined known problem and look at the tools that that language provides or technology that you're trying to learn and try to solve it. And along the way, you will learn those new concepts that the technology provides, right? It's called learning by example. And this is what we'll do here and what we'll do in the Scala training that will be upcoming in the next couple of months, right? Again, we'll pick few problems, we'll walk through the concepts, and along the way we will learn those new concepts, and also it'll be a good revision about the problem solving and algorithms that we will encounter, okay? And that's what we'll do today. We'll pick one specific problem from data clustering, and we'll try to solve it, okay? But before we do that, let's talk a little bit about functional language. How do we define what's a functional language? And it's surprisingly quite difficult to define, to find a simple definition that says this is a functional language, this is not. And the reason why it's quite hard is because basically the designers of functional languages try to come up with their own definition that suits their language the best, right? So there is no one simple definition. And if you just Google it, it will tell you a functional language is one that models computation as mathematical function. This doesn't really help us much, right? Because it's quite simplistic, it's quite abstract, and it's kind of defining something with another definition, right? But perhaps we're asking the wrong question, right? We shouldn't be asking what is a functional language. We should be asking what is a functional program? What does a functional program look like? Because after all, it's not the language that is functional, but it's the way you develop. Right? And for me, in my opinion, there's 3 functional principles that are in the next 3 slides that one should follow while developing functionally. There's a lot more, of course, but we'll go through the 3 main ones, the 3 more important in my view, okay? Principle number 1 is to try to reduce side effects as much as possible. Okay, what's a side effect? This is a function where it has a side effect. A side effect is when you're storing state, whether it's in a global variable, a class attribute, or a database. When you're storing state, it's a side effect, right? There's an example of a function over there that is storing the I integer. It's incrementing it each time, but it's storing it in a global variable, right? And that's a local attribute, and that's storing state. Every time you're going to call this function, it's going to store state every time you call it. Whereas opposed to this function, the cubed x, which is just that power of 3 of x, is not storing any local state, right? It doesn't have any side effects. It's an example of a function without a side effect. All right. The second principle is try to develop your function or methods as referentially transparent as possible. Referentially transparent is a big word. I don't know. It means I don't know. Maybe it might scare people that don't have experience of functional languages, but it's something quite simple actually. The function over there, if you pass in hello world as 2 parameters, as string A and string B of that function, right? It will return the string concatenated together. If for those 2 inputs we replace the body of the function with just the constant hello world, the behavior of the program is not affected at all. And that's the definition of what's referentially transparent. If you can replace the body of the function with a constant for the same inputs, the behavior of the program is not modified at all. And that, as a result of that, you get functions that when you call them with the same inputs, they will always return the same outputs. This is what we call sometimes idempotency, okay? But idempotency is a little bit more tricky because the term idempotency is a little bit more strict. Okay, in functional languages and in mathematics, idempotency means something even more strict than this. That's why it's referential transparent. But you can think about it in that way too, right? This is another function, for example, that is not referential transparent. Why? You call it multiple times with the same inputs, it's going to return you a different output, right? That's because it's doing a random number generation inside. I don't know, I gave the stupid example over there of a scale where you put always the same apple on top of it, it will always give you the same reading. Whereas a toaster, you put always the same bread, but it will burn it to a different degree depending on its mood, right? Okay, and the third and final most important principle is to try to be immutable as much as possible. We already have experience of this, right? If you're programming in Java, JavaScript, and a lot of other languages, they have certain classes and objects that are immutable. For example, in Java, there's a string, right? Once you create it, you cannot modify a string. You just have to, if you want something, you want to modify something, you need to create a new one, right? This is taking that concept to the extreme, saying everything should be immutable, including complex data structures, like that, for example, right? Like a linked list, for example. Let's say we have that linked list, and you want to add an extra item at the end of it. Okay, in a non-immutable data structure, or immutable data structure, you would just add it at the end. You would modify the linked list and have the extra object at the back. If you're using an immutable data structure, it will create, you end up with two linked lists. The original one, completely untouched, right? And a new one with that extra item at the back of it, okay? That's what immutable is, of course. You know this, right? But this is just applying it to everything, to all data structures, all objects that you will use in the language. Why should we bother? There's performance issues sometimes when you're using these immutable objects. There's extra, you need to think differently when you're developing in this kind of fashion. Why should we bother programming functionally? There's some advantages, of course, right? Immutability reduces race conditions when you're programming, programming in multi-threaded way or multi-processing. If you're using immutable data structures that cannot change, you'll be fine, right? Because none of the threads are stepping over each other's toes, right? So if you're using the same linked list, for example, and you're modifying it, you need to have a lot of exclusive locks while you're modifying. Whereas if you're using immutable data structures, you don't have that problem. Functional programming also tends to write more concise codes, and as a result of that, you have less complex codes and fewer bugs. Once you're used to it and you're doing it properly, right? And I think, in my view, the biggest advantage is that the code readability improves, right? You'll see, we'll see an example later, that an algorithm, when you write it in a normal iterative way, it's quite difficult to read as opposed to the same thing written in a functional manner. Once you're used to it and once you're doing it properly, basically. And why should we choose Scala as a functional language? Scala is not the only language out there to develop functionally, but there's some advantages. First of all, well, mainly is that it lets you write non-functional code. This is great. Why? Because it lets you gradually step into the functional world. You start writing Java-like code if you want, simply without semicolons, maybe, right? And then you slowly start introducing more and more functional concepts in it until you're writing fully functional code. Okay? Other languages are more strict. They don't let you write non-functional code. So you step much, the transition is much more sudden, right? Whereas with Scala it's more gradual. And the other advantage is that it has good integration with Java. Right? You can use whatever libraries you're using already with Java, and they will work, right? Unlike some other languages. Okay, this is the second part of the presentation now, where we will pick not a single laugh about the cow. Yeah, it's impressive. Anyway, we'll pick a particular algorithm and we'll try to implement it in Scala. Okay. So before we write the algorithm, I want to explain what the problem is that we're trying to solve. Okay. And in order to do that, I'm going to get help from this guy, John, over here. He says hi. Okay. And over here, we also have another person, Sarah. She also says hi. Yeah. God, you guys are really serious. Okay, so these are very two different people, and they lead very different lives. John over here is a doctor. He works in a hospital, regular shifts, crazy hours, right? Sarah over here, she works in a bank, normal hours, 9 to 5. And she has quite a free weekends, and she just has a normal office job, okay? John over here likes to de-stress on the weekends after a week full of whatever doctors do, yeah, in hospital. He likes to de-stress, sit down in front of his TV and watch his favorite team playing, right? With beer in one hand and his mobile phone in the other. They both share a common hobby, right? They both like to bet on an online betting website. And yeah, so John likes to watch his game, and with his mobile phone, he likes to bet, right? He likes to bet on his favorite team, I don't know, FC Porto, whatever, right? Okay, no? Anyway, and he just enjoys it, right? He just does it for fun. Sarah is a very different type of bettor. On the weekends, she sits down, she watches the market prices, she writes bots, she writes algorithms, tries to predict the market prices, tries to beat the market basically, tries to manage the risks. And yeah, she does that programmatically. She writes all these clever software to do that. As you can tell, they're very different betting patterns, right? If we as a betting company want to attract these two types of people, or want to market things to these type of people, we need to recognize that we need to show them different types of adverts. Okay, for John, we just show them adverts about Porto, okay? Or, I don't know, try to hit his emotional side to football, okay? Whereas Sarah, we need to have a different marketing campaign for her. We need to show her, I don't know, maybe discounts on market prices, or a smart new API that we've developed that is quite fast, that gives her market analytics and that kind of stuff. And that's great, but we need to be able to differentiate the Johns from the Sarah. How are we going to do that, right? We already have a huge amount of betting data in our database. It's about trying to find which ones are the Johns and the Sarah. And now Sarah is going to show us how we can do that, okay? She flies too, okay? So we have a chart over there, X and Y axis. On the Y axis, we have the bet amount, how much you bet on each bet on average. On the Y axis, we have bets per day, how many bets you place on a particular typical weekend day. Okay, Sarah would be down there. She places a small amount, typical 2-3 euros every bet. However, they're very frequent. She bets, I don't know, hundreds of bets every Saturday and Sunday, right? Whereas John would be on the other side. He places typically 100, 200 euros on a bet, but he only places 1 or 2 on a weekend. They're very different betting patterns in that way, right? We can recognize that. We can recognize them in this manner. And if we had to plot more betting data on this chart, we would see that all our clients would cluster towards one end or the other. Right? They're either traders or just emotional, like just having fun, right? People. Of course, this is a very simplistic view. Of course, we wouldn't just have 2 clusters, right? But this is very simplistic. We want to write an algorithm to be able to differentiate those 2 clusters, to be able to tell these are Johns, these are Sarahs. We need to display these adverts to Johns, these adverts to Sarah. Okay? We want our algorithm to recognize those clusters, but it needs to be able to support more than that, right? So here we're only showing 2 dimensions, because if we had more, we wouldn't be able to plot it easily, right? I'm keeping it simple for the presentation. But in reality, we would have more variables, more dimensions. For example, we would measure the profit and loss for each client, or the age and gender, for example, like a mix of these. The bet diversity, how many different sports they're betting. And the other thing we want from the algorithm, apart from being multidimensional to support my own, it needs to support not just 2 clusters, but n clusters, right? We might have another cluster up here, and these are the ones that bet loads per day and bet huge amount. These are the ones swimming in money. They don't know what to do with all that money, right? They're just throwing it away. And over here, we would have the other group where they place very rarely and small bets too. These are, I call them the hipster bettors because they drive a scooter. No? Okay. Anyway, and so the algorithm needs to also not just pick those 2 clusters, but pick n clusters, however many clusters we decide. And let's try to build this algorithm slowly together. But first, let's talk a little bit of how it works, right? Let's go back to the presentation. Okay, the algorithm, yeah. Some of you might have heard about it. It's called k-means. Some of you might have done it at university. Otherwise, I don't know, maybe seen it online. It's a clustering algorithm. It was invented by Stuart Lloyd while working at Bell Labs. You like my icons? No? Okay. And it's an unsupervised learning algorithm. Okay, so it means you give it a bunch of data, and the algorithm will try to find patterns in it. Unlike supervised algorithms where you train them, where you say, this is the Sarah, this is the Jones, learn from this, right? And it will then use that information for data sets that it hasn't seen. This is unsupervised, where you give it a bunch of data and it will just try to find patterns. Okay, and the algorithm works by using this concept of clusters and centroids, right? So they have, each cluster has a centroid, kind of the average center of a cluster, and it uses this concept to try to find the clusters. It goes through 2 phases, constantly going through these 2 phases. One phase is the assignment, and the other is the recentering. And it goes back and forth through these phases until it converges. Let's walk through an example. Let's say this is the same chart that we saw before, and let's say we have this sample data, okay? The initial step of the algorithm is to pick 2 random points out of this data set and assign a centroid on each, right? So here we have centroid A and B, right? These will be the centroids of our initial 2 clusters. And we go through the first assignment phase, where we go through every single point of, so we go through this point and that point, every single point of that, and try to figure out which centroid is the closest. In this case, that particular point is closer to B, of course, right? So we assign it to B. We say this is closer to B. In this case, we say this is closer to A than to B, so we assign it to A. And we keep on doing this through every single point. To hurry up in this presentation, there's an easy geometric trick we can use, and it only works for 2D. And we can draw a straight line, then a perpendicular line to that straight line, and anything anything top of that line is closer to point A. I don't need to go through the geometric proof, right? But you guys, it's intuitive. You can tell anything north, anything on top of that line is closer to A, anything south of that line is closer to B. So you get that cluster belonging to A and that cluster belonging to B. Yeah, you guys understand that? Okay? So we have already 2 clusters. Now we go into the recentering state, right? The recentering phase, the other phase that we saw on the previous slide. And that is by going through every single point that we have in each cluster and finding the average x and y axis and recentering that particular centroid. And we do the same for B, okay? Remember, this is the average x and y axis, not the median, right? And now we go back to so we recenter it, and we go back to the reassignment phase. So again, we can do this visually, straight line, perpendicular, anything on the right belongs to A, anything on the left belongs to B. Okay, boom, there's the 2 clusters. I have a small mistake here on the slide. These should be in here, okay? Just, if you see that, they should be in there. I missed it. Okay, so again, we go back to the recentering part. We move the centroid A to that place, to the center of that cluster, to average center, yeah, and the same thing on B. And again, now we go to the reassignment phase. straight line, perpendicular, anything on the right belongs to A, anything on the left belongs to B. Yeah? And now we have our two clusters. We do the recentering, and now if we do again the reassignment, we see that nothing changes. No point moves clusters, and the centroid does not move either, right? That means our algorithm has converged. That's the end of the k-means. We've discovered which ones are the Sarahs, which ones are the Johns, okay? Oh, well, we have discovered two clusters in our data. And that's it. That's how our algorithm works. Let's try now to implement this in Scala, okay? Before we see the actual code, let's talk about the structures that we need, the objects that we need to create that will hold our data. Okay, of course we need a point, which will be, well, the cross that we saw on the previous chart, and it just needs the x and y integer. I'm using x and y integers. In reality, for the betting example that we had in the beginning, we could use bets per day and, amount, right? But I'm just keeping it generic and use the x and y integer. And to create that, I'm going to create, oops, I pressed the wrong button. I'm going to create a new worksheet just to show you how we're going to do this. I don't know if you've ever used the Scala worksheet. Some of you have already used Scala, of course, and you know what Scala worksheets are, but they're a quick way to try things out in Scala without actually doing any code, right? Just to see, you see the result quite quickly. So here I'm creating a case class point. For those of you that have never developed in Scala before, case classes are like POJOs in Java. They just hold data. And you have a bunch of methods generated with them, included in them, like the toString and the equals. So here I've created a case class with the constructor x and y, constructor and fields x and y, which are both integers. And I'm creating the first point at 20,30. Okay? As I said, you get a lot of free methods with them. So I can do, for example, the getter in Scala, in Java, you do .a.getX, whereas in Scala, you do .a.x. Okay? You just access the attribute directly. I'm here creating a new point B, and I can do .a equals point B. Yeah? Because the two equals method is included already in the case class. Okay? This is, for a lot of you, this is not new. You've used case classes many times before, but I promise it will get harder than this, okay? So yeah, this is now I'm changing the points, and the equals is false. And now I can do .a. I think I'm doing .a.toString. This is another method that's already included, and the hash code, and there's others, of course. Right? This is just to show a few of them. ToString is that, the hash code is that. Okay, that's our first structure, the point. The next thing we need is the cluster case class, the cluster object, right? Which will hold the centroid, the center of that cluster, and a bag of points. Okay, so we need the centroid, which is also of type points, which will have an x and y axis, and the list of points. Okay, and here I'm going to do it. I was thinking of writing this while presenting, but last time I did it, it was a lot of mistakes, and I thought it's easier to just record it and talk through it. Yeah. So, so I'm creating a cluster here, again with the centroid on the front, and points, the list of points. This is basically what we saw on the slide. It's a list of type point, okay, and that's the case class defined. Now, here I'm creating an example of a cluster. Value cluster1 equals, you notice I don't need to write the new, like Java in Scala, right? Because they're case classes, I can omit the new keyword in front. You can write it if you want, it doesn't make a difference. Right, so I'm creating a cluster example over here with 100, 100, and a few points inside. This is just to show you how to use these case classes, okay? Yeah, that's compiled. I can also create another, yeah, that's the point inside, and that's a bag of points that you have as the second attribute, okay? If anyone is not following this and wants me to slow down or repeat, please let me know, yeah? We have time. I'm going to create another example of a cluster here, And I'm going to call it cluster 2. And this time I'm going to create it without any points, with an empty bag of points inside, right? An empty list of points. And I can do that by removing everything in there. Okay? And that is just a cluster without any points. Instead of having an empty list, I can also write nil. This is a syntax in Scala that nil just represents an empty list. Okay? Instead of writing empty list. I can also provide the default constructor in there, default variable, to say if that particular parameter is omitted from when you initialize the class, default it to an empty list, to nil. And that's what happens, right? When you don't write it, it defaults to nil. Okay? It defaults to an empty list, exactly. So those are the two structures. We also need a way to, so our algorithm will step through a number of steps until it converges, right? In order to see that going through. I'm going to call each one of these a cluster batch. A cluster batch is just a list of clusters. Again, this is trying to make it simpler so we don't have a list of lists of points. Okay? That's why we're creating these structures. At the end, once the algorithm finishes, we're going to have a history of these cluster batches, right? So we're going to have a list of cluster batches. And that's quite easy to create. It's just a case class called cluster batch, yeah, which will have a list of clusters inside. Okay, so now we have all the structures that we need. We can focus on the algorithm itself. Okay? Okay. Yes, before we start the algorithm, we need to try to find out how we can work out the distance between 2 points. And this is quite easy. We just use Pythagoras. Okay? That's the formula for Pythagoras. Right? It's not rocket science. We replace replace a and b with x and y. Okay, replace it in there. And we're going to have a method in the point that says distance to another point, and it will just use that. Okay, I'll go quite quick through this. I'm going to define a function in the case class, which we'll call it distance2, and it will take another point, right? Point, yeah, call it other, which will be a type point. Okay, and I put that mathematical function that we saw on the previous slide in here. Again, this is Pythagoras, right? It's quite simple. You do mat.square root, mat.power, other.x minus this.x to the power of 2, plus the same thing on the y. This is primary school maths, okay? Maybe secondary, I think. So that's how to find the distance between 2 points. And after I write that, I'm going to show a few examples just to prove that this is working. Okay? Replace the x with the y over there. Okay? And now it's just a matter of calling that function. Right? So I'm going to create 2 points. I don't know what I'm doing there. Yeah, I'm creating 2 points. Point A equals, and I'll give it 2 coordinates, 100, 100. And I'm going to copy that point with exactly the same coordinates, and I'm going to try to find the distance to the same point. What will be the answer of that? 0. Yeah, of course, right? This is just a quick way to see that it's kind of working. Then I'll change the point B coordinate, and we'll see what happens, right? So the distance is 0, and point A equals point B equals true, of course. Now I'm changing the coordinates and running this again, and it will give me a non-zero distance, right? 53 units, whatever they are. Okay, so we have the distance defined. Now let's go into the details of the actual k-means algorithm. 3 important steps in this algorithm. The first one is the initialization part, where we pick n random points from our data set, and we assign them to the initial clusters, to the initial centroids, okay? Step number 2, we assign each point that we have in our set to the closest centroid, okay? And then the other one is to recenter each centroid within that cluster that we have. And we keep on doing step 2 and 3, while the centroids keep on changing. If the centroids don't move, we say that's converged, and we exit the algorithm. Okay, let's see how we can implement the first step, and I'm going to show you this, how we can do it by an example. Here I'm writing a list of my team members: Vera, Eduardo, Vitor, João, Diogo, and Hugo. Yeah, I forgot the interns, sorry, they're not here, so it doesn't count. And so these will be kind of our points, right? We'll use this analogy to build the first function. Let's say I want to change them to uppercase. That's quite easy. We use the transform function. We use .map to uppercase. So it will go through every item in that list and change it into uppercase, right? So now everyone is in capital letters. All right. Let's say I want to pick the first 2 out of that list. The way I can do that, in Scala is any list I can do maps.take and provide a number. So take 2, it's going to pick the first 2 of that list. So Vera and Eduardo, right? Now, this is the extra bit. How can I randomly shuffle that list? There's a function in Scala called random.shuffle. Yeah? And I can give it a list, and it will basically shuffle the list, right? So you can see over there, Vera stayed on the front, but everyone else got shuffled around. They're not in the same position. And in fact, if I run it again, which I'm going to do now, if I run it again, you'll see that now Vitor is on the front, right? They're all shuffled around. Yeah, I run it again, and now João is on the front. And I can now combine the 3 together. I can do random.shuffle, names, take 2, take the first 2, and change them into uppercase. Okay, so it will pick the first 2 of a randomly shuffled list and change them to uppercase. Okay, and now we have João and Diogo on the front. Yeah, this is just like selecting 2 of them, 2 of that list at random and changing them. Now Hugo and Vitor, every time I run it, it picks two more. And I can use this technique to pick 2 random points from our list of points, right? And that's what I'm going to do. There's a function called I'm writing a function called initial clusters that takes all points, which is a list of points, and it's going to return our initial set of clusters. It also needs n, the number of clusters we want to find or want to generate, right? And it's going to return a list of those initial clusters. And it can do that quite easily by using the same technique. We do random.shuffle, all points, we shuffle all the points, and we do take the first 2, and map, transform those 2 points by creating an empty cluster with just the centroid. We do that by doing map, give it a function that takes a point as an argument, and creates a cluster with that point. Okay? Remember that the cluster has a default argument, right? So if you just give it the point as a centroid, you don't need to give it an empty list of points. Okay? So that's that's step 1 of our k-means algorithm, the initial clusters. Okay? I'm going to skip the second part because it's a little bit harder. So we're going to do the recentering part. Okay, now, again, we need to write a new function for this. Okay, so I'm creating a few random points over here just to show you, so we can build it gradually, the recentering function. Okay, I think I'm putting a triangle over there. Okay, so let's say I want to change, let me pause this. Let's say I want to change point a comma x, right? If the value of a dot x is 10, right? Which is that one. How do I go about changing x? You cannot, right? The answer is you cannot change it. You cannot say a dot x equals 15. It will not compile, right? You cannot do that. This is because Scala tries to encourage immutability, right? So you can't, once you create a case class, you cannot just say, oh, you know what, I'm going to change this attribute. It doesn't let you do that unless you override it, unless you go on the case class and says, I don't want this to be immutable. All right, so the way to do it is to create a copy of it. To create a copy with the change attribute. So you say d, another point, is a dot copy, but I want a different value of x. Copy it exactly as it is, and I want a different value of x. And now x is 15. Notice that the y-axis stayed exactly the same, 10, right? And in fact, a.x also stayed exactly the same. The object stayed exactly the same, of course. It wasn't modified, right? So you have a is 15, sorry, a is 10, and b is 15, okay? This is to encourage immutability. Now, if I want to find the average centroid of those 4 points, how do I do that, right? I can put them in a list. I extract the x-axis, right? And now we have a list of x-axis, which is the 10, 20, 10, 15 up there. Yeah, you can see it. And I just need to find the average of it, right? I can find the sum by doing dot sum. Yeah, it will give me the sum of those 4 items, which is 55. And I just need to divide by 4, right? Divide by the size of the points. And that's the average x-axis, points.size. Yeah. And that will give me the integer. It's been truncated, not truncated, it's been floored, but it's the average integer again. Okay? And now the recentering function takes in a list of clusters that it wants to recenter and returns a new copy of that list of clusters. Right? It cannot modify those clusters because they're immutable, so it needs to return a new one. And that's what it's doing there. Right? So that's the signature. We say clusters.map, so transform each one of those clusters. And yeah, you give it a function, see, the cluster itself. And we use the average technique that we used over there. We say x average equals c, the cluster, dot points, dot map, the x-axis, find the sum, and divide by the size of the number of points, right? And we do the same for the y-axis. Okay? Now, we just need to create a copy of the cluster itself that was passed in. So we do c.copy. And we specify a new centroid, which will be the average x-axis and the average y-axis. Okay? Is everyone following? Okay, see people nodding. I hope they're not like nodding asleep, but yeah, okay. So that's the average, that's the recentering using the average points. Okay? Now, the last bit of the algorithm before we put everything together, which is probably the one that is a little bit more difficult, right? Here we reassign every single point that we have to the closest centroid, right? So we need to assign them to the closest centroid in that cluster. So let's try to do this, okay? Again, I'm going to create, making some space first. Then I'm going to create a bunch of points just so we can try things out, right? So we can build the function gradually together, okay? Bunch of points over there, and I'm going to create there's a list of points. I'm going to create 2 sample clusters. I'm going to call them cluster A and cluster B with 2 different centroid points. Yeah, the first centroid is at 50,50, 55,55, and it doesn't have any points assigned to it. Okay? And the second, yeah, remember, if you don't specify the list of points, it's empty, it's nil. And the second cluster, cluster B, will be at 70,70. Now our task is to go through that list, yeah, and find which ones are closer to this point and which ones are closer to this point, yeah, to separate them, right? To say these particular points are closer to cluster A, these particular points are closer to cluster B. This is our task of this function. So we put both clusters in a list, and we go through every single one of the points, we transform them, we do all points.map, we transform them, and we say, first thing we can do is say, how far are you from cluster A? Right, so we do cluster A, dot centroid, dot distance to that particular point. This will simply output a list of how far each point is to cluster A, right? So that's the list. So The first point, 50, 50, is 7 units away from 55, 55. The second one is 0. In fact, it's on the same place, right? And you have a list of distances of every single point to that cluster, to the cluster A. Right? In fact, yeah, 0, 0, because it's 55, 55, the same as that one. Okay, so we're getting slowly there, right? What about if I want to find the distances to both clusters, to both cluster A and cluster B? I can replace that. Instead of cluster A, I can say clusters, which is our list of clusters containing A and B, and we map it, and we transform it again, right? We do a dot map. And now we'll have a list of lists. You can tell this is getting a little bit more complex every time, right? So now we have a list of lists, right? The first item in the inner list will be the distance to cluster A, yeah, there. And the second item is the distance to cluster B. Right, so the first point is 7 units to cluster A and 28 units to cluster B. Okay, so in that case, it should choose cluster A because it's closer. Okay, and you can see there's loads of nested lists. How do we choose the minimum one? It's easy. Instead of using dot map over there, we do a really useful function called minimum by. Right, and this will choose the cluster that is closer, that has a minimum value of distance, right? And if we run this, we'll see that for the first point, it shows the cluster that is at point 55, cluster A, right? It's great, right? This is kind of doing all the work for us. And yeah, for the second point, it also chose the same cluster, the one at 55. It did the same for the third point, I think, yeah. 55 because it's closer, and then from there onwards it chooses cluster B, which is at 70, 70. All right. So it has chosen the one that's closer, but it's not enough. We need to group the points to say these particular points are closer to cluster A, these particular points are closer to cluster B. We need to group them. How do we do that? We change that map, that transform function, into a group by. Right? Sorry. And now we have a map. And the contents of that map is like 2 entries, right? 2 key value entries, one with cluster A, and the list of points associated to it, right? Those that are closer to it. And the other entry is cluster B, and the list of points that are closer to it. This is it, right? The one-liner we wrote, the most difficult part of this algorithm. Yeah. We just need to now transform that map into, and put all the points into the clusters themselves. And the way we can do that is we assign this map into a variable. Yeah. We go to the list of clusters, which is we call it clusters, and we transform that. And for each cluster, we find that value in the map and create a new cluster with the map in it. So we copy it, and we say points are whatever you find in the map that we've just generated. We do points by cluster dot get or else C. This will look into the map, okay, into the hash map. Or if you don't find anything, put an empty list. Okay, and that's it. That's our second part of the algorithm. We just need to wrap these 2 lines in a function, and we're done for that part. Okay, you can see the output over there. You have the first cluster, which has a centroid of 55, 55, and those bag of points that belong to it, that are closer to that centroid. Okay, and the second cluster, which is at 70, 70, has those three other points. Okay. This is possibly the most difficult function of this entire presentation, right? So if you understood this, you're fine. If we put it around, you just need to put it around the function. That's all we need to do now. We call it, I think I call it assignment, yep. And yeah, it accepts all the points that we have to deal with, and the current list of clusters. Okay, and it returns the modified list of clusters, the ones that were assigned, the ones that were assigned with the points, okay? We're just wrapping it around the function here. That's all we're doing. Okay? That's it. Deleting the lines. Those are the 3 steps that our algorithm needs. The only thing left to do is to put them all together and writing that while condition at the end to say stop switching between these 2 states if you have converged. And this is what we're going to do now. It's also surprisingly not that simple to do, but we'll build it slowly together. Let's say we want to generate this sequence of numbers in Scala, right? 1, 2, 4, 8, 16. Every time we're multiplying by 2. Geometric progression, right? So we do stream.iterate starting at 1. This is very different than the Java stream, okay? It's not exact. It's not the same. So we do stream.iterate starting from 1, and each time we do I times 2. We multiply it by 2. And this will generate an infinite stream. So we need to say, okay, take only the first 10 and convert them to list and output them so we can see it. Right? And it's generating that particular sequence out there. Okay? We can say take 20 instead of 10, and it will generate 20. Okay? Goes up to a huge number. All right. We can, instead of saying take, we can say take while instead. We can say take while and provide a particular number where we want to stop. We can say, take while, and this takes a function instead of a number. And we say take while I is less than 20. Sorry, it's less than 1 out of 5. And it will stop. I don't know how to type over there. And it will stop at 1 out of 4. There you go. 1 out of 4. All right, what if we want to output a list containing the index of the list? Remember, this is a normal list. Each item in that list has an index. So this is 0, 1, 2, 3, etc., right? What if we want to output the actual index of that list? So there's a useful function called zip with index. And this will change our output from just one single value. We'll change into what we call a tuple containing the value and the index. Okay? And now we have to change the function to contain both the value and the index, right? We'll still say stop when I is greater than 1 out of 5, but now we have the index with it, right? 0, 1, 2, 3, etc. Okay? That is what is called a tuple. Those 2 numbers you see in the brackets are tuple in Scala. Okay? And we're going to use this technique, these 3 lines, to put our functions together, and we stop consuming from our functions, right? Here, I can also change the condition to stop taking, to keep on taking from the stream while the index is less than 5, right? So I stopped at the 5th item, the 6th item. Okay, so let's write down the final function, which is, we call it k-means, which accepts a list of points, and n, the number of clusters it wants to find in those points. And it's going to output a list of cluster batch. Remember, a cluster batch is just a step through our iterations, right? So we're going to have all the steps in the end. All right, and the first thing we do is we call, remember, step 1 of our slides is to initialize with random clusters from the points. And we have the initial batch, which we call the initial clusters. This is the first function that we wrote. Okay, you're using those random team names that we developed in the beginning, okay? Team member names. And we put that as the first step in our cluster batch, all right? Remember, cluster batch is just a list of clusters. I'm tired of saying clusters. Okay, so as the initial step, the second step is the one that needs to be in the while loop, the one that we keep on repeating until it converges. Okay, and we're going to use the same technique. Stream.iterate, starting from an initial state, which is our initial batch. And at each step, we're going to call those 2 other functions that we developed. And we have the cluster batch, the current cluster batch, and the first function we call is the assignment. Okay, so we say assigned clusters equals assignment. We pass it all the points, And this is just wiring the functions inside, right? We call, and we pass in the clusters. And then is the recentering step. we create a variable called recentered, and we call the recentering function. Okay? Using the assigned clusters. And now it's just a matter of wrapping the recentered into a cluster batch. And that's kind of our loop. But there is no stopping condition, right? We're going to keep on generating at infinity. We just need to tell it when to stop, when it has converged. And we're going to use the same technique that we used up here. We're going to say zip with index and keep on taking from that infinite stream while, and what's the condition we need to put? We need to keep on taking while the centroids are still changing. And this is the clever bit, right? We're going to have the current batch, a function that takes in the current batch, and the index that it's at. And the condition is when the current batch, when you extract the centroid of the current batch, is not equal. You keep on taking while the current batch centroids are not equal to the previous one. And we do that by extracting the centroids, and we say not equal to steps index minus 1. It's kind of doing a recursive call, right? Like keep on taking to the previous until the previous clusters are not. Keep on taking while the previous centroids are not the same as the current ones. Okay, that's it. That's our stopping condition. Now, all that's need to do is we just need to transform this, because remember, our signature is a list of clusters, and here we have a list of cluster tuple, right? Cluster index tuple. We just need to extract just the cluster batch. Yeah, and that's just doing a mapping to extract the cluster batch, and we do a toList. And that's it. That's our 3 functions put together with a stopping condition, with a converging condition. Okay, now I'm just tidying up and putting it on one page. Right? And yeah, all that's left to do now is to try it out. Okay, just a quick summary. We have the k-means function up there that takes in a list of points and a number of clusters and returns a history of cluster batches. We call the initial clusters first. Then, in a loop, in an infinite loop, we start from initial batch, and we do the assignment phase and the recentering. And we keep on doing this while the centroids are still changing. Okay? While the current centroid and the previous one are still changing. And that's it. That's our function. Who wants to try it out? I need a volunteer to try this out here. This is a play application with a simple web interface that we call our function. We just need to draw dots on it, like this. Yeah. And then hit this button over here. Yeah, here I'll show you. And it will try to, let's draw a bit more. We'll try to find out where the clusters are. Okay, so those 2 crosses are the 2 centroids, right?
Step 1?
Exactly. This is step 2, I think. Step 1, the initial random thing is not shown. It's only after the first assignment is done. And then we can step through. There you go. It's just 2 steps. It converges really quickly. You can also choose how many groups you want. I've limited to 4, basically because you run out of space otherwise. But, come on. So someone wants to try it? Yeah?
What is that groups thing?
So I'll show you. So let's say you put...
You can find multiple clusters?
Exactly. More than 2, right? Let's say you want... I should have called it clusters, but not groups. Let's say you have 4 groups. Now, the k-means algorithm is not always guaranteed to converge, right? It depends where you start as the initial centroid, right? There's a lot more advanced techniques. This is one of the most basic, right? It's what I could show here in an hour, right? Without wasting. So there's a chance that we won't converge, but There you go. See, for example, it picked the wrong initial cluster, so I don't think it will converge. In fact, let's try it again. See, it didn't. It all depends which, there you go, no it did. It all depends which initial clusters it picks and how far away the clusters are. Does anyone want to give it a go? Not much enthusiasm here.
How do you find the multiple groups? Do you just recursively run the same clusters?
So the multiple groups, you give it, the function that we've developed before, you give it 3 as an input. Say, I want to find 3 clusters in my data set. Right? So there you go. This is probably a good example. So the initial centroid was actually probably up here, and now the second step it moved. You see it stepping through. There you go, conversion. Yeah. Yeah, that's basically it. Nobody wants to try it? Yeah. Okay. Sure. The recentering function is here. Did you find a bug in it? If that's the case, don't tell me. No, I'm joking. Yeah, so it's going through the points in the cluster, summing up the x-axis, and finding the average, and doing the same for the y-axis. And then copying the current cluster and assigning a new centroid to it. Yeah? Anyone has more questions about the algorithm?
First to centroids that you have in the example. You will put some points there.
Yeah.
Put some points
Hey, come try it out. Come on.
Shouldn't be these 2 centroids in one point
No,
that we
yeah.
define.
So
Or it's
initially, the
random.
first random selection, it picks a point. Yes, you're right. But then, when it's when it's recentering, it could be on a center, an average, right?
In this step, it already
Yeah,
recentered?
it already did the first
Okay.
loop. It already did the first loop of that. Basically, this. Yeah, I built this in like 15 minutes, right? I didn't have a lot of time to spare on this, but it's using the same function that I've shown you on the screen. Okay. I'll put this on GitLab, and I'll send the link for anyone that was interested in trying it out. Yeah. Okay, so quick chat about the training. Tiago has left, but anyway. The training, we're planning maybe in a couple of months' time to have 4 or 5 half days. It will be focusing on Scala, but it will be similar things to this, right? We'll pick lots of these problems, maybe not on data mining, but like things about, like, I don't know, merge sorting or binary trees or things like that, things we've done at university, right? And we'll try to implement them in Scala, right? It's learning by example. Of course, we'll talk about concepts, we'll talk how to create, I don't know, variables, case classes, collections, etc. And we'll use those tools to solve problems, okay? But we'll focus mainly on functional principles, which are the hardest, right? Anyone can learn any language in here, I'm sure. But if you're not used to functional programming, that's the hardest step. That's the hardest transition, okay? If you're just used to writing procedural and non-functional code. It will also serve as a good data structures and algorithm refresher, right? And for those of you that I have forgotten at least some of the university stuff that we did. It will be a good refresher. Okay, that's all I have for you guys. Please visit my blog, leave comments and feedback.
Can you share it on the channel?
Share the codes or... Yeah, we're recording this, I hope. And I'll put the link on the channel, yeah. Anyone has more questions? Thank you guys. Yeah.